I will explain incompressible flow over finite wings, chapter 5 from Anderson book. Flow over finite wing is different from flow over airfoil because wing has a third dimension. And such properties, geometrical properties, will impact also on performance and aerodynamic properties on the real wing. We will also see performance for the wing in the same way that we saw for the airfoil. Lift coefficient, drag coefficient, momentum coefficient. And the model we will discuss today will involve also so-called third dimension or downwash of velocity. First of all, let's talk about physics of flow around the wing. Typical wing is presented on figure 3. It has in its cross-section, any arbitrary cross-section, can be represented as airfoil. Okay, I will try to draw this airfoil as a cross-section. Okay, probably too thick. Let's try to make airfoil as a cross-section, two-dimensional, extended to third dimension, will form a wing. With respect to airfoil, wing has more geometrical parameters that are used to describe its geometry. First of all, it's a wingspan, which is usually denoted by B. It's the distance between two tips of the wing. There is also a wing root, is size of chord on the center of the wing, where fuselage is present. There is a wing tip, which is described by size of chord on the end of the wing. Usually, wing root is bigger, wing tip is smaller, but not always. There are different types of wings, where, for example, wing can be made of constant chord size. Such wings are usually called rectangular wings. It's very similar geometry, rectangular geometry. But in most cases, we will find that on the tip, size of chord airfoil is smaller than on the root. Because it's a three-dimensional structure, it has these wing tips, and it has also flow around the wing tip. Flow around the wing tip is called trailing vortex, presented on the lower figure, on the bottom of figure 3. And it appears due to not equilibrium pressure on the lower and on the upper side of the wing. We remember that to create a lift, usually airfoil needs to have, not nice, probably. Airfoil needs to have higher pressure on the lower side, P lower, and lower pressure on the upper side. Due to pressure difference and area on the wing, we have lift. So this effect of pressure difference applied to a wing creates a flow around the tip of the wing. So flow from higher pressure region goes to lower pressure region around the wing, goes around, so creating a vortex. Since flow is moving, this vortex also will move in such a way on the tip of the wing. Okay, this flow picture is symmetric, so we can repeat in a similar way. Two vortexes, trailing vortexes on the wing always exist. Such vortexes are physical response of nature due to difference of pressure, and this trailing vortex always will appear independently on the wing geometry. Or let's say differently, there is no wing which doesn't have a vortex on its tip. Vortex can be more stronger, less stronger, weaker, and this relation between energies, or this relation between energies transformed to lift and lost energies are giving us efficiency, definition of efficiency of the wing. This we will see very soon from calculation point of view. So there is such a movement of a streamline, which you can see on the upper part of figure 3. Streamline on the bottom surface is moving more to external side of the wing, and the streamline on the top surface moves to the center of the wing because of velocity, different velocity directions. A vortex appear. Such vortex can be observed not just schematically or analytically, which is presented on figure 4, but such vortex can be seen also on experiment. Here on figure 5, experimentally visualized streamlines by a smoke in the wind tunnel, where you can see that vortex structure appears. Also, such a vortex structure can be observed on numerical simulation. Here, this wing you can see here, it's some simulation I did in past just to see how flow will behave around the wing, and we see that streamlines visualized started from the wing, formed for such a nice vortex structure. Vortex by itself is something that cause extra losses on the wing. Vortex is something that we would like to mitigate. There are several ways to reduce its strengths. Most are devoted to profiling of appropriate shaping of the wing. So for different wing shapes, vortex strengths are different. Also, there are some winglets or structures on the tip of the wing which are reducing the circulation and or decrease the formation of wing tip vortex. About question of winglets, I think we can find a lot on real pictures of real airplanes. A lot of modern airplanes use winglets to improve their efficiency. Once we are talking about efficiency, we talk about very small number. It's near 1–2% of efficiency, so not so high. Let's see from geometrical point of view how we define parameters which would be involved in calculation of the wing. We have a wing cross section, which is airfoil section of finite wing. We can see on figure 6. Here on this airfoil, we also see alpha, angle of attack. It's the angle between velocity v infinite, velocity direction, and which is horizontal, and chord of our wing, alpha. And this alpha is divided into two angles, alpha efficient or effective, and alpha I, induced. So since vortex is present, wing tip vortex is present we always represent these losses related to this vortex as some quantity or velocity associated with this vortex. For us, this velocity is defined on figure 6 as W. Is called downwash velocity, is always related to infinite velocity. Once we find relation between these two velocities, W velocity is perpendicular and is directed downwards. So this is why downwash velocity. Since these two velocity vectors are present, one perpendicular to another, we can define alpha I, or induced angle of attack associated with the wing. So induced angle of attack gives us proportion between infinite velocity and downwash velocity, or energy which we have coming to our wing and losses of energy due to wing geometry. So I hope more or less clear that V infinite and W are having same relation as forces. For example, here force diagram. Sorry. Here force diagram is also present. We have a lift force defined, L. Right? We have DI, which is induced drag, and between them we have alpha I, induced angle of attack. Here lift is not, because of some reason, very strange, because of some reason lift is not horizontal. Yeah, lift is not horizontal. Sorry, lift is not vertical. Lift is not vertical. Between induced drag and the lift force, we have angle, same induced angle of attack as between velocity and downwash velocity. DI, induced drag, is an extra drag we have on the wing that is characterizing for us losses on the wing due to presence of wing tip vortex. General roadmap for chapter 5 is the following: is general features of finite wing aerodynamics, downwash, effective angle of attack, and induced drag. These concepts I just presented you in relation between them. Then we go to additional tools needed for finite wing analysis. They are chord vortex filament, they are Biot-Savart law and Helmholtz theorem, vortex theorem, which are used to build numerical, let's say, numerical or analytical method of calculation of the wing, similar to method of calculation of airfoil by vortex sheet. Then we go to different methods of analysis when we apply these three tools. They are Prandtl's classical lifting line theory, the simplest method allowing us to calculate lift on the wing. Then a modern numerical lifting line method, which allows to calculate wings of more complex geometry. And also I discussed limitations of this method in this chapter. Then lifting surface theory, which allowed to calculate three-dimensional wings. And modern vortex Lutz numerical method is just an introduction that allows to calculate practically any shape aerodynamic three-dimensional bodies and obtain lift over these complex shaped three-dimensional bodies, not just the wing by itself, but any arbitrary body. So increasing complexity from Prandtl's classical lifting line theory for the simplest wing until any shape on a modern numerical method. Increasing complexity step by step. First of all, we define drag on the wing. drag on the wing is presented on equation 4, 5.4. CD is equal to drag coefficient on the airfoil plus induced drag coefficient. So drag coefficient, which is characterized for bidimensional flow, and induced drag coefficient, which is characterized for three-dimensional. So we must take into account both of these drag coefficients to calculate total drag coefficient over the wing. Induced drag coefficient will be defined similar to ordinary drag coefficient. We, instead of drag force, will use induced drag force. And as a reference, we will use dynamic pressure and area of the wing. S is the area of the wing, not chord anymore, is a planar area of the wing. And the drag coefficient for classical drag coefficient, as we know before, presented on equation 5.2, composed of two drags. One drag is associated with friction, dF, with the presence of boundary layer and the shear stress, and second part associated with the pressure, dP, drag created by pressure forces. You remember that between dF and dP could be some relation between them. For example, for airfoils, we know that dF is much more significant than dP. For blunt bodies is opposite. For example, for cylinder, dF is much smaller than dP. Depend on shape of body, relation between these forces would be different. For airfoil, more important for us friction than pressure distribution for drag calculation. I hope it's clear with drag coefficient for the wing, right? We must consider both. Part which we used for calculation of airfoil and also part just associated with the vortex forming on the tip of the wing. And the second concept, let's say, we go to theorems, right? Vortex filament, the Biot-Savart law, Helmholtz theorems. They are both go in one package. Here is the Biot-Savart law. What is very interesting that this law is representing to us change of velocity or differential of velocity at any arbitrary point P due to presence of vortex filament of strength gamma. This similar concept we already had in bidimensional flow. Now it's applied to three-dimensional flow. So let's see that velocity at any arbitrary point P will will change due to presence of constant strength of vortex gamma or circulation of vortex, right? Reverse proportional to a constant 4 pi, then would be multiplied by size of each piece of this vortex, multiplied by our distance. It's a vector product, distance, let's say vector, and divided by cubic distance. This Biot-Savart law is very similar to electromagnetic theory, where we see a relation between, I think, magnetic field and electrical properties of a wire. I think it's a current, right? I here. Very similar. This Biot-Savart law has no direct relation to physical process, is not obtained from integration or transformation of flow equations according to Anderson. This Biot-Savart law is more an approximation of process than solution of flow equations. So it's a sort of a model which fits very nicely in existing physical law. It corresponds to a physical process, but is not obtained from the transformation of flow equations. We can apply this Biot-Savart law to calculate our velocity once we integrate left and right side of equation 5. On the left side, we will obtain velocity created by vortex. On the right side, we will integrate all the vortex filament. This is done on equation 7. On the left side, we have velocity. On the right side, we have integral. Our vortex filament is infinite according to, I think, Helmholtz theorem. This vortex filament cannot have end in, cannot finish inside space. It will be or going to infinity or will finish on the surface of the body. From equation 7 to equation 8 is transformation from Cartesian to polar coordinates, where equation 9a, b, and c are showing this transformation from linear to polar, from Cartesian to polar coordinates. So equation 10 for us is a solution of previously expressed equation 8, where we assume that vortex filament is a straight line. So it has just a linear shape, not arbitrary in space, is a line. And in such case, solution can be found. Solution shown on equation 10, saying that velocity created by vortex, how do you call it? Vortex filament, linear one, with known strengths gamma, will be in three-dimensional space, will be calculated proportionally to strength of this vortex and reverse proportional to the normal distance from this vortex to arbitrary point P. So here also equation 10 and this equation in square, I am marking here by red color, showing to us this dependence. Velocity, strength, and reverse proportional to normal or closest distance between line and arbitrary point P. And at this point P, we calculate our velocity. Velocity is directed on direction according to the direction of vortex. For example, direction of vortex is clockwise here, and the point is placed on horizontal line between a vortex sheet or vortex filament. So velocity is directed downwards. For us, it's easy because this velocity will be a downwash velocity in our future discussion. Okay, this is again a concept showing the picture of vortex filament and velocity at any arbitrary point created by this vortex filament. We see that velocity is reverse proportional to the distance. So closer to the vortex filament, velocity goes to infinite. Far from this vortex filament, velocity goes to 0. Now we will go from this definition of a vortex sheet or vortex filament to calculation of the wing. We know that on the wing we have lift distributed in a way similar to figure 11. Here we can see sketch and the lift distribution along the span of the wing. On the center of the wing, we have maximum possible lift. Then on the tip of the wing, lift is 0, reducing to 0. This curvature or shape of lift distribution will depend on shape of the wing, geometry of the wing, and mostly on geometry and the profile of airfoil on the wing. But we know general behavior then would be typical to figure 11 would be maximum, and this maximum will be, say, distributed on some part of the wing, would be close to maximum, and then would be sharply going down this wing lift. At tip of the wing would be 0. Why 0? Because on the lower and upper side of the wing, on the tip, pressure on the top and on the bottom would be same at the end of the wing. So pressure difference would be 0. This is why lift on the tip would be also 0. Such distribution gives us a way to calculate analytically lift distribution when we expect more or less similar behavior of lift function over the wing. There are two Helmholtz theorems which we are using, as I told you already. First one is strength of a vortex filament is constant along its length. So we will use vortex filament of constant strength, which simplifies a lot solution. So we do not see a function anymore. We can bring outside of integral function strength of vortex. And the second one is a vortex filament cannot end in a fluid. It must extend to boundaries of the fluid, which are in plus minus infinite, or can form a closed path. Okay, Prandtl, very nice picture. Historical thought. Prandtl's lifting line theory is the following. Prandtl suggested that downwash velocity or velocity represents losses on the trailing vortex would be calculated in the following way, as you see on equation 12. Here, gamma is circulation of the vortex. B is length or size of the wing. The coordinate of the wing is from minus b divided by 2 to b divided by 2. In total is b, length of the wing. And y is a coordinate along the wing. Can be positive or can be negative. Then simplifying equation 12, we conclude in equation 13 that says to us what could be the downwash velocity over the wing. This flow picture is corresponding to a vortex structure called shore vortex, represented on the right part of figure 12. This vortex is having one part which lies on the center of the airfoil, bound vortex. Here we can see it over here. And then on the tips of the wing, this vortex filament rotates 90 degrees and goes to infinity and is called free trailing vortex on the one on another side of the wing, free trailing vortex. This vortex has constant strength, as I told you, so we integrate constant value, and the vortex is composed of 3 parts, right? One going parallel to the wing and 2 going to infinity perpendicular to the main axis of the wing. This representation of downwash velocity is good, but not perfect. It was the first attempt to calculate the wing analytically. Let's see again this function presented on previous slide, equation 12 and 13, and graphical representation of this downwash velocity. We see that analyzing this function, we conclude that downwash velocity on the tip of the wing would be equal to minus infinite value. This happens because this part of equation, b divided by 2 square minus y square, would go to 0. So this is why w, downwash velocity, will be minus infinite. This is the main problem of such model. And also, since a real flow is not a real distribution of lift and real distribution of downwash velocity is not so linear, that is presented by Prandtl lifting by Prandtl theory is not explaining exactly distribution of the lift over this wing. To improve, this happens because we have just constant value of gamma on this vortex. Since gamma is constant, it means that lift over the wing is a constant. So if I build here, if I extend, and if I draw lift according to Prandtl's lifting line theory, we will have a constant lift over the wing along the wingspan, which is not true. As we saw, we needed to receive something similar to this distribution, a real lift distribution. And this is what Prandtl's theory is proposing to us, constant value, very different from real distribution. To improve this theory, we can use a concept of superposition of Horseshoe vortexes presented on figure 14, which is a composition of different vortexes which stay on the same place on the axis of the wing. So we have vortex gamma 1 of strength gamma 1. This vortex is extended, of course, over all the wing, and it goes from the tip of the wing. Then there is a vortex gamma 2. I will use another color just to identify. This is another vortex, gamma 2, okay, and it goes like this according to blue color, which I mark. And there is, let's say, the third one probably, okay, would be a green color, maybe more thicker. Okay, this is vortex number 3. Which stays at position on the center. So once we have 3 Horseshoe vortexes representing our wing, we already see something similar to real distribution of lift. I would like to remind you that distribution of gamma is similar to distribution of lift because we have Kuta-Zhukovsky theorem, which says to us the following, that lift would be proportional to gamma multiplied by density and multiplied by velocity. So since velocity and density are constant, we have a proportionality between lift and the circulation. Curve of gamma is proportional to the curve of lift. So here we have superposition of 3 vortexes. Once we increase number of vortexes, we can describe with any precision we need distribution of lift over real wing. For example, here, multiplying infinite number of vortexes, we can calculate any shape of gamma we would like to have, or we have on real wing. Going from one vortex to infinite number of vortexes, we have to integrate downwash velocity along all these vortexes. So equation 14 for one vortex becomes equation 15 for infinite number of vortexes. We have integral on the left and on the right side of this equation. Here, 1 divided by pi is 1 divided by 4 pi is a constant outside of integral, and the gamma is a function. Distribution of gamma is a function that is inside the integral because it's a function of y direction, and we are integrating by y direction. Just a moment. Okay, I'm here again. Please let me know if you have some questions. I will answer. For now, I see no questions and comments, or you can also ask by voice. So equation 15 is representing to us relation between downwash velocity and the circulation over the wing. Now let's try to solve this equation by some way. I hope you already understood that there is no analytical solution for any arbitrary shape of the wing. But there is always a way approximation, which is called numerical solution, which can be used to obtain data. This solution, some transformation must be done to obtain this solution. First of all, we will write that, okay, equation 15 is same from previous slide. We will introduce a relation between downwash velocity and infinite velocity as induced angle of attack. Arctangent of induced angle of attack is, arctangent of velocity ratio is equal to induced angle of attack. And with the assumption that alpha I is very small, similar to 0, we use instead of tangent or arctangent of function, we use just an argument of this function. So we will say that induced angle of attack, since it's small, would be equal to a ratio between downwash velocity and the infinite velocity. Of course, it's directed downwards. This is why it has minus in before this ratio. Okay, downwash velocity in equation 17 is taken from equation 15. So this value here is taken from this equation. And once we substitute equation 15 inside equation 17, we will obtain equation 18, saying to us function or a function how to calculate induced angle of attack for a wing. We see that induced angle of attack now will be a function of y coordinate and can be calculated for any point once we know distribution of gamma or we know distribution of lift, because lift and gamma are related one to another. So for us, it's not important if we have gamma or lift. In all this story, I forgot to tell you what is the significance of efficient or effective angle of attack. Effective angle of attack is the angle of attack which is calculated as the difference between real angle of attack and induced angle of attack once we subtract one from another. Let's go back to the first slide. And we can see this relation here. According to this geometrical definition, we will see that alpha, effective would be equal to alpha minus alpha I, where alpha is geometrical angle of attack direction between flow and chord, and the induced angle of attack represents to us losses on the wing. So effective angle of attack can also always be calculated as difference between these two angles. And as you saw on my previous discussion, induced angle of attack can be calculated from distribution of circulation over the wing. And as a result, also effective angle of attack can be found as a function of gamma over the wing coordinate. For each coordinate y, induced angle of attack will be different, and this is why effective angle of attack will also be different. Why effective angle of attack for us is important? Because it's the angle of attack which we use to calculate lift. Now, according to equation 19, if we look carefully, CL would be a product of A0, lift slope, multiplied by effective angle of attack minus alpha L0, which is angle of attack at which lift is equal to 0. Instead of using alpha for airfoil, we are not using alpha anymore. We are using effective angle of attack, and because induced angle of attack we already lost, and we created a vortex with that induced angle of attack, so we cannot use it anymore. Instead of total angle of attack, we use effective angle of attack, which is always smaller than geometrical alpha. Once we simplify this for thin airfoil, according to thin airfoil theory, if you remember from previous chapter, we already found that for thin symmetric airfoil, CL was 2 pi alpha for symmetric one, and for cambered airfoil was CL 2 pi alpha minus alpha L0. For the wing, we have absolutely the same idea, because wing utilizes airfoil for which we already elaborated theory of calculation. So we can find very similar definition of lift coefficient. This was for b-dimensional case, and this one is for 3-dimensional case. Very similar formula. Instead of alpha, we use alpha effective, just with this difference, right? I hope you remember now that alpha exists for b-dimensional case, alpha effective exists for 3-dimensional case. Please do not calculate just with alpha your wings. Calculate induced angle of attack first, according to equation 18, and then subtract from geometrical alpha induced angle of attack, and use this effective angle of attack for your calculation. Once you obtain lift coefficient in equation 19, you can use this coefficient to calculate total lift. As a classical definition from our previous discussion that lift would be proportional to dynamic pressure, chord size multiplied by lift coefficient. This chord size, it looks, it's chord size, so we obtain L prime for each 1 meter, and then we multiply by length of the wing in meters, right? So this L prime is Newton per meter dimension, Newton per meter. And then when we multiply by size of the wing, for example, a wing has 3 meter wingspan, we will obtain amount of newtons that sustain our wing. And same we can do according to Kuta-Zhukovsky theorem, right part of equation 20 that I wrote you on my previous slide. Density multiplied by velocity multiplied by circulation gives lift. Okay, and lift coefficient calculated as a function of circulation. I think it's, yeah. From equation 20, we elaborate equation 21. We see that lift coefficient would be 2 times of circulation divided by infinite velocity and chord of the wing, or chord of the airfoil at the point where we calculate lift coefficient. Lift coefficient would be a function of y, of coordinate. Once we find it, we can also rewrite effective angle of attack. Our effective angle of attack would be calculated by equation 22. It will have 2 parts. And one part would be devoted to a lift created by the, let me see. Yeah, this is a lift from equation 19. It's the same as we had in equation 19, but we rewrote from equation 19, we obtain equation 22 once we substitute lift coefficient as a function. So we combine equation 19 and 21, and we obtain equation 22. Effective angle of attack. And from geometrical relations, we already knew that effective angle of attack is the difference between alpha and alpha induced. Now we combine equation 22 and equation 5.1 inside one equation. Also, we introduce here, instead of induced angle of attack AI, I use equation 518, which we can see over here, definition of induced angle of attack, and we obtain equation 523, which says to us relation allowing to calculate geometrical angle of attack, or okay, not allowing to calculate this angle of attack by defining geometrical angle of attack as a sum of 3 components: effective angle of attack, induced angle of attack, and alpha angle of attack at 0 lift. This equation 523 is the equation which has just one unknown. This unknown is gamma. Unfortunately, we cannot solve this equation directly because it's integral differential equation. But with the several simplifications, several assumptions, we can try to solve it. Solution. after we obtain would allow us to calculate lift. Once we solve this equation, we will obtain gamma. Then we can use it to calculate lift over its relative lift per 1 meter of airfoil, or per 1 meter of wing, sorry. We will be able to calculate total lift on the wing by integrating the previous function. And also from equation 25, we will be able to calculate total lift over the wing, and then splitting the forces, we can calculate induced drag over the wing. Assuming that induced angle of attack has a small value, instead of sine alpha, we will use just alpha. In equation 27, we will find a relation between induced drag on the wing and induced lift on the wing. Okay. And also with several transformations taking into account calculation of this induced wing as integrating, okay, integrating lift per unit span over the wing, we will be capable to obtain induced drag, and using instead of lift circulation, we can do same calculation, and drag coefficient can be calculated once we calculate drag and put in drag coefficient equation. Okay, left side, and same relation on the right side the equation. All this would be possible once we solve equation 23, which gives us relation between physical angle of attack and circulation over the wing. As I told you, this equation is not possible to solve analytically, but it is possible to solve with several assumptions or solve it numerically. One simple way to solve that equation is to assume some specific shape of the wing, for example, elliptical wing shape. Once we have elliptical wing shape, we can suppose that circulation over elliptical wing. What is elliptical wing? Let's go further and I will show you what is it just before we discuss the result. So this is the elliptical wing, which shape is corresponding to an elliptical shape, geometrical shape. Okay. Let's go back. We assume that for the elliptical wing, we have distribution of circulation given in equation 31. Once we have this gamma, we can take a derivative by y-coordinate. It's a simple relation. We obtain equation 32, the derivative of gamma. And according to definition of downwash velocity by Prandtl lifting line theory, we obtain equation 33. And then equation 33 in Cartesian coordinates is transformed to polar coordinates and solved. Such integral of equation 34 can be found analytically. And this analytical solution is shown on equation 535, saying to us that downwash velocity would be a ratio, would be negative value, but ratio of circulation over the wing, the maximum value, gamma 0, over the wing divided by 2 length of the wing. Since we know downwash velocity and we know infinite velocity, we find ratio between them and we find induced angle of attack, which is now maximum circulation over the elliptical wing divided by two sides of the wing and infinite velocity. Okay, having this solution, we can calculate all other properties. As was shown on previous formulas, we calculate lift over elliptical wing integrating circulation function. And equation 37 would be found solution of this equation in the polar coordinates as equation 38. We will see that lift on elliptical wing would be proportional to maximum circulation over the wing multiplied by infinite density and velocity multiplied by size of the wing and pi divided by 4. Since we have a wing of known size, and because of this wing of known size and will have a known value of lift, we can always define circulation or maximum circulation over the wing in equation 39. We re-express equation 38 and find that maximum circulation on the wing will be 4 times of lift force on this wing divided by infinite density velocity product by size of the wing and pi. Some parameters here can these parameters also make part of lift coefficient. This equation 39 can be rewritten in terms of lift coefficient instead of just using lift value. And as a result, equation 41, induced angle of attack, written before as a ratio between velocities, can be now written as a function of lift coefficient, size of or area of the wing and size of the wing. Induced angle of attack will be proportional to area of the wing, lift coefficient, and reverse proportional to pi and square root of size of the wing in square. We remember that ratio between b in square divided by s was already defined in theory of aerodynamics as aspect ratio. Right, aspect ratio is the ratio between, okay, this is the wing we have, or something close to elliptical wing with size b, and here we have square of size b by b. So this is aspect ratio. Area of the wing or area of square divided by area of the wing will be also bigger than 1. And once we introduce inside equation 41 this aspect ratio definition, we will see that induced angle of attack will be proportional to lift coefficient and reverse proportional to aspect ratio. This is very important. This is a very important result. This is why it's in square or in rectangular shape, because it says to us that losses on the real wing would be always proportional to lift coefficient. Bigger is lift coefficient, bigger would be losses on the real wing. And they would be reverse proportional to aspect ratio. Bigger is the aspect ratio, smaller would be losses associated with induced effect or induced downwash velocity. Okay, that's it. Then we can calculate analytically also induced drag coefficient according to equation 42, which can be solved. This is a general integral equation which could be solved, and solution is presented on equation 43. We see that induced drag coefficient will be on a wing would be proportional to lift coefficient in square divided by pi and divided by aspect ratio. I think this formula 43 is even more important than the previous one. It says to us very interesting result that any wing will have losses. These losses would be proportional to lift you are generated on this wing. More lift you gain, more losses you will have. It's not possible to increase the lift coefficient and decrease losses for the same wing. You can decrease losses by changing aspect ratio, not by increasing lift coefficient, but by increasing aspect ratio. And more longer will be your wing, smaller will be losses. I think this definition is telling to us in which direction we would like to work once we are designing efficient flight vehicles. Same time, look from other points of view. Look from point of view that big aspect ratio airplanes probably would not be so fast, right? Because they will suffer probably bigger stresses than small wing airplanes. I mean, long wing is should be more resistant than the short wing, right? So there is always a balance between aspect ratio, size of the wing, and losses we would like to have or losses we could have on our airplane. I think equation 43 is a culmination of aerodynamics, at least aerodynamics for the wings, saying to us that losses on the wing will always exist. No matter how you improve your aerodynamic structure, you will need to have at least to fight with this induced drag existing just because of the wing geometry. Okay, longer wing, you need less energy to fly. Shorter wing, smaller aspect ratio, you need more energy to apply on your engine to fly with the same velocity, same characteristics. So this is why planners or airplanes which could fly long distances, low velocity airplanes, they have very long wings because induced drag in such case could be significantly reduced. Okay, but also do not forget about this numerator, CL in square. For example, you improve a little lift coefficient, but your drag coefficient also will be increased. Okay, do not search for infinitely high values of lift coefficient. Very high lift coefficient values have several disadvantages. Need always to search for the balance between lift and drag. And for the airplane, also must be paid attention on integrity and strength of the wing. Right? From aerodynamic point of view, infinite wing would be the best, but from a real structural problem point of view of designing of a real airplane, you cannot use too big wing. Probably aspect ratio would be very limited. Okay, I would like to say several comments about applicability of this theory which we talked. It's very nicely could be used in rectangular wings, straight wings, wings of classical shape, right? For high aspect ratio wings and for low aspect ratio wings, but cannot be used for example, delta wings or triangular wings, because in such case, since shape changes drastically, cannot be achieved good accuracy of calculation. So when we are more far from classical rectangular wings, more we are far from classical Prandtl's theory, more bigger would be the error associated with this problem of geometry. But about this thing, I think we will speak a bit in future, probably today or next class. Let's see. Please let me know if you have some questions. I would like to make a break of probably 1 minute just to relax a bit because my voice is tired. Let's make a break, 1 minute, and then we continue. And please, you can ask your questions, type in comments meanwhile. Okay, I will turn off my microphone for 1 minute. Okay, I'm here again. Thank you for waiting. I see no comments in the chat, so probably I would continue. I would like to tell you that these concept and models are currently implemented in software of preliminary wing design. You can find on internet this free software like XFoil, XFLR5. Okay, this is, as I told you already before, illustration of elliptic wing and associated circulation on the wing, which is also elliptic, according to a formula which we saw previously. And now I would like to say several words about a general lift distribution. Equation which you saw previously, 523 from our previous discussion, giving a relation, just a moment, giving a relation between geometrical angle of attack and alpha L0 angle of attack at zero lift coefficient, also giving relation to circulation over airfoil and behavior of circulation over airfoil along the wing can be solved analytically. Let's say analytically, it's too much, probably can be solved numerically. Once we substitute some quantities defined in this equation, for example, we will transform Cartesian coordinates to polar coordinates in order to use Fourier series to express our functions in Fourier series, equation 48, 49. And due to this transformation, we obtain equation 50 and 51 is equivalent to equation 23, but rewritten in polar coordinates and rewritten as a Fourier series function gamma and gamma derivative. I will not stop deeply how this equation is solved because I think you understand that these equations can be solved purely in a mathematical way, have nothing related to aerodynamics. So if you like mathematical physics, you can follow this discussion. I will not explain here. Everyone study mathematics at the university, and I will not ask you in future how these solutions can be obtained, because it's a purely mathematical question. For me, more important that you know which methods are used and which solutions and which consequences we can see, what consequences we can see from solution of these equations, which physical process can be described, right? Not the specific methods of solution. This solution we will give to mathematicians, specialists in this area, and they elaborate for us very nice instruments and tools for aerodynamic research. Our work is to provide research in aerodynamics. This is what we do. As a result of previous equation, we will see function of lift coefficient. You can see it can be found analytical in equation 53. Lift coefficient over, okay, let's go back, general lift distribution. This is a wing of a general shape, any shape we want, almost any shape, not exactly any shape, would be function presented here on equation 53. This would be function proportional to aspect ratio. Higher is the aspect ratio, higher is the lift. Would be proportional to pi coefficient and would be proportional to A1 is the constant once we solve equation number 51. Once we solve equation number 51, we receive first coefficient from Fourier series, and this first coefficient is used to calculate lift coefficient. Or vice versa, we can use this equation in both ways. If we know lift coefficient for our wing CL, we know aspect ratio for our wing, we can calculate this A1 for our wing and can use it for other wings for other aspect ratios. Okay, changing aspect ratio, we proportionally change the lift coefficient, but we need to maintain profile of the wing and we need to maintain the cross-section and structure of the wing proportional. We can just, let's say, change scale in y direction of the wing axis. Doing this, we can maintain same value of coefficient A1, and we can calculate lift for different aspect ratios, which is extremely useful for real practical application. Obtain experimentally A1, and for all similar wings, you will have possibility to predict lift coefficient. By the same way, we can do calculation for induced drag coefficient. I will skip a lot because it's a lot of transformations, mathematical transformations. I will just go to the final here. Okay. There is a definition of induced drag coefficient, as you can see on equation 61. That drag coefficient, induced drag coefficient, would be proportional to lift coefficient in square, same as we had for elliptic wing or rectangular wing. Reverse proportional to aspect ratio, absolutely same as we had for elliptic wing. And also should be multiplied by 1 plus delta, where delta is a drag factor. Drag factor or obtained experimentally or calculated mathematically according to equation presented near to equation 561, this delta factor. Very soon we will see graphical, more or less values of this delta factor are given. Or we can rewrite this equation 61 in form of equation 62, where instead of drag factor, we use a span efficiency factor, E, defined as 1 divided by 1 plus del. Equation 62. Okay, let me skip, and I will go back to that slides very soon. I just would like to show you this drag factor value for different aspect ratios, for different taper ratios. Delta can be a small value, but is a positive value between 0 and 0.16. For different aspect ratios, for smaller aspect ratios, this delta is smaller. For high aspect ratio, delta is higher, but in general, it's not so big, right? So we can see it's more or less increases induced drag coefficient in average. Okay, I can do average somewhere here near 5%. Near 5%. Taper ratio, I would like to remind you that taper ratio is a ratio between chord size on the tip of the wing and on the root of the wing. This taper ratio is always smaller than 1, is saying for us how different is this size. This is the T, okay? This is on the wing, right? The flow goes in this direction here. And this is CR on the root. Always smaller than 1. We see that there is an optimal value of drag factor, smallest value, almost 0, maybe 1-2% increase of induced drag for taper ratio close to 0.3, 0.35, more or less. 0.3, 0.35 gives us the best value of drag factor, and as a result, we have smallest value of induced drag coefficient. Okay, so this I think is very useful graphics. But we must remember one important thing, that since all influence on all in aerodynamics, this graphics is typical not for all possible airfoils. Just for some specific airfoils, for different airfoils, this graphic would be different as well. But at least figure 20 gives to us estimate some approximation, some average value of possible drag factor, right, which is not so high. Maybe 5%, maybe 10% at most. Let's go back here. Figure 18 shows to us various plane forms for straight wings. The most famous is so-called elliptic wing, which you can see on figure 19. This elliptic wing was extremely famous on the Second World War. You can see a lot of historical movies with this type of wing airplanes. Nowadays, they are not used anymore because of several reasons. I think main reason is the cost. These wings are much more costly to manufacture because of shape of the wing. And nowadays, there are other ways to increase the efficiency of the wing, like performant shape of airfoil already gives much better performance, and also swept wings, which allow to fly faster than elliptic wing. So elliptic wings have several advantages, from which are high value of lift, right? But several disadvantages as cost. For my opinion, there are also maybe some other disadvantages you can find in the literature. So if you find something interesting about this type of wing, please, I think everyone will be happy to hear and to know something new from this historical perspective. Aerodynamics has long, more than 100 years old history. And the tapered wing, something that you already saw on the previous formulas, right? Tapered wing, extremely interesting because it allows to have reduced value of induced drag. It's simple from a manufacturing point of view, just a linear shape, right? Having some increased performance with respect to rectangular wing. Rectangular wing by itself is not the best solution nowadays because rectangular wing has the biggest value of induced drag and losses associated with induced drag. Rectangular wing has problem with the maximum flight velocity, so it can be used for low velocity applications. If you would like to fly fast, is not possible because of nature of the wing, and the wingtip vortex is strong, so you need to have high power engine, not so efficient with respect to other types of the wings. Each structure has its advantages and disadvantages, and there is no best ever structure. Right? So any structure will have some good and not so good aspects. Actually, our next topic is aspect ratio effect, aspect ratio, AR. In this topic, Anderson explains to reader what is the method to calculate wing with the different aspect ratios. It's this similar thing I already explained to you, that we can use similar wings, just changing aspect ratio, changing induced drag. Explaining this in terms of experimental data. This is very interesting data taken long time ago in 1921, more than 100 years ago. You can see here that the axis, it's lift coefficient and drag coefficient, but you can see that those days lift coefficient, drag coefficient were denoted by very different values like CA and CW, and they are not in the form of coefficient, they are form of some dimensional parameter, because classical lift and drag coefficients, which we know today, change from 0 to 1 more or less, right? They were elaborated during many decades. An example how calculation from one aspect ratio to another aspect ratio can be done in a very simple way in order to obtain lift and drag coefficient associated to a wing. You can see that we can recalculate one wing to another wing according to this diagram here. Prandtl used different wings, and they are basically represented on the same curve. So we can use any wing to calculate other wing of different aspect ratio, and you will have very nice accuracy of recalculation of one wing to another. I mean, wing performance, right? Lift and induced drag values, not flow around wing. No one talks about flow pattern. We are talking about integral average characteristics like lift coefficient, drag, and induced drag values. Okay. Comparison between different types of wings. We know that for infinite wing or airfoil, lift coefficient is higher. For finite wing or elliptic finite wing, lift coefficient is smaller. So lift slope is smaller. There is a way to predict this lift coefficient slope. It would be related to lift coefficient on airfoil and would be related to aspect ratio on the wing. For elliptic wing and in general for any other wing. For any other wing, but I think not any other wing. They mean finite wing in general. It can be applied for rectangular wing or tapered wing, not any wing of any geometry. Lifting line theory is quite limited on application. It works only with simple wings. Unfortunately, complex shape wings, especially aerodynamically twisted wing, when we change from one section to another profile of airfoil, or we change angle of attack from one section to another, which allows us to create extremely efficient wing, this theory cannot calculate. This theory calculates only simple structures, as usual, typical for any analytical model. Okay, another example of recalculation using Prandtl's wing area, rectangular wing data, variation of lift coefficient with angle of attack of our different wings and scaled to aspect ratio 5. So another example how to calculate from one wing aspect ratio to another wing aspect ratio, proving that theory of this recalculation is working. Some design box presented, and I hope you can study at home. And this here is represented to us two regimes of flight: cruise flight and takeoff. What happens on cruise flight? Induced drag always exists, as we know, but relation between parasite drag and induced drag for takeoff and cruise flight are different. We know parasite drag is pressure drag and shear stress drag. These two drags which we had in airfoil. So this parasite drag is, let me write here, dF plus dP. And this induced drag would be di. Okay. Parasite drag always exists, and induced drag also will exist. Since takeoff is not a nominal operation of any airfoil with increased angle of attack, induced drag during takeoff regime will be significant and could be more significant than parasite drag. So this is why during takeoff, airplane must use much higher power than it uses during cruise flight. Only for people who flew on airplane, you've heard during takeoff, engine produce too much noise, right? So too much thrust. This is because must compensate induced drag, which is much higher during takeoff than during cruise flight. A relation between induced drag and let me see here, induced drag and lift coefficient is given on equation 72. I think this equation we already saw previously. Yeah, on some other page, we see that induced drag is linearly proportional to lift coefficient in square. It means that once we have high angle of attack, we have high lift coefficient, we have high induced drag. And then recalculating lift coefficient from point of view of weight of airplane, we see that induced drag, according to equation 74, would be proportional to weight of airplane. Since it's proportional to lift coefficient, of course, lift and weight should be compensated on takeoff, and drag force would be proportional to weight force of the airplane. Equation 74. Higher weight, higher drag. Okay, I would like to propose to start this question of numerical non-lifting line method next time. We will need to start from fresh, and it will require some time to explain. So please let me know if you have some questions today I can answer. And we meet next time on Thursday. And I hope on Friday we also have class. Okay. Please tell me if you have questions to discuss today. I can still answer. About Friday class, one more announcement. I think we must talk about simulation, since main focus is on work 2 or finishing work 2. Would be very important to answer your questions about numerical simulation, CFD, if some problems. Do not afraid to show if you have some problems inside your simulation. It's normal. If you have problem, probably your colleague also have same problem or similar problem. I will answer not just for one person, but for all who are interested to know more about numerical simulation. Another comment I would like to give you, that recently I returned back from ANSYS 22 to ANSYS 21, even though if ANSYS license is expiring very soon in I think in July, because ANSYS 22 was giving several errors. Maybe it's just on my machine, but I could not work quite well on ANSYS 22. So I returned back to ANSYS 21, and it looks like is more stable. More stable, it means it doesn't crash so frequently. It also crashes as usual, but not so often as ANSYS 22. On ANSYS 22, I had several errors on mesh calculation, on mesh definition, on simulation, just crash without any messages, without any report. So if you have also frequent crashes of your ANSYS workbench, you can go downgrade and use ANSYS 2021 R2, which is much more stable than ANSYS 22 R1. I don't know why it happens. The first time in many years this problem happens, but pay attention when you simulate, and if it crashes often, probably it's better to go back to ANSYS 21. Okay, I see no questions for now. Let's meet on Thursday and continue discussion on aerodynamics. I think we can finish chapter 5 very soon, and then we could continue with chapter 6, and then with very few classes you could pay more attention or more on simulation than on theory of aerodynamics. Thank you for participation today, and see you next time. Goodbye.